Radioactivity. In this third nuclear physics video, we will discuss a natural phenomenon in which atoms emit radiations to attain stability. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. In the last video, we spoke about the stability of nuclei and we saw that not all nuclei are stable. Atomic nuclei that do not have enough binding energy to hold the nucleus together due to an excess of either protons or neutrons are going to attempt to reach stability by ejecting nucleons, protons or neutrons, as well as other particles, or by releasing energy in other forms. Radioactivity, decay, also known as nuclear decay or radioactivity, is the process by which an unstable atomic nucleus loses energy in an attempt to become stable by emitting charged particles or protons, such as alpha particles, beta particles, or gamma rays. These particles and photons emitted by unstable nuclei are called radiation. Radiation is energy transmitted through space in the form of electromagnetic waves or energetic particles. Main features of radioactivity. It is purely a nuclear phenomenon due to the instability of the nucleus. The unstable nucleus undergoes spontaneous disintegration. The process continues till a stable nucleus is obtained. It is independent of external factors such as pressure, temperature, state of substance, electrical field, magnetic field, and catalyst. The process is uncontrollable using these factors. The unstable nucleus undergoing disintegration is called a parent nucleus, and the new nucleus formed is known as daughter nucleus. This daughter nucleus will usually be of a different chemical element from the original isotope. During alpha, beta, and gamma radioactive decay, two simple conservation rules come into play. Nucleon number A is always conserved. Proton number Z is always conserved. Radioactive decay will change one nucleus to another if the daughter nucleus has a greater nuclear binding energy than the parent nucleus. The difference in binding energy comparing the before and after states determines which decays are energetically possible and which are not. We now discuss the most common forms of radiation in more detail. Alpha decay. When a nucleus undergoes alpha decay, it loses two protons and two neutrons, and therefore a different nucleus is formed. The alpha decay can be written symbolically as follows. In alpha decay, the mass number of the daughter nucleus is far less than that of the parent nucleus, while the atomic number decreases by 2. Alpha decay occurs in heavy nuclei. Typically, Z is greater than 83, when the ratio of neutrons to protons in the nucleus is too high. The mass of the parent nucleus is greater than the mass of the daughter nucleus, plus the mass of the particle. As there is a difference in mass, we can use the conservation of energy and Einstein's mass-energy relation to obtain the energy released in the alpha decay process as follows. The mass difference appears as kinetic energy, which is carried away by the particle and the recoiling daughter nucleus. Most of the kinetic energy is carried away by the alpha particle because it is much less massive than the daughter nucleus. Let's solve one example to make the theory clearer. If the parent nucleus emits an alpha particle, it loses 2 protons and 2 neutrons. Therefore, Z decreases by 2 and A decreases by 4. The decay can be written as follows. We take the formula above to calculate the disintegration energy in this process. We substitute the values given and perform the calculations. We consider the parent nucleus is an isolated system that decays into an alpha particle and a daughter nucleus. The system is isolated in terms of both energy and momentum. Before disintegration, the parent nucleus can be assumed to be at rest, so the total momentum was 0. After disintegration, the total vector momentum must still be 0. So the magnitude of the alpha particle's momentum must equal the magnitude of the daughter's momentum. We solve this equation for the speed of the alpha particle and substitute it into the equation of disintegration energy. After some algebra, we obtain the kinetic energy of the daughter nucleus and the kinetic energy of the alpha particles. We can see that alpha particle carries off 98% of the total kinetic energy. Beta decay is the process of converting an unstable nucleus to a stable nucleus by releasing electrons or positrons. There are 3 forms of beta decay: beta minus, beta plus, and electron capture. Now let's get somewhat detailed into that. In beta minus decay, an electron and an antineutrino are emitted by a nucleus. The number A of nucleons remains the same, while the proton number Z increased by 1, and the neutron number decreased by 1. The general equation representing beta minus decay is given as follows. Inside the nucleus, a neutron changes to a proton, and to conserve the charge in the process, it emits an electron. Beta minus particle emission occurs when the ratio of neutrons to protons in the nucleus is too high and the mass of the parent atom is greater than that of the daughter atom. In other words, the nucleus has too many neutrons compared to the number of protons. Let's see how the beta minus decay works. Every carbon atom has 6 protons, so carbon 14 has 8 neutrons. It is unstable, and its ratio of neutrons to protons is approximately 1.33. So this atom satisfies the conditions for the occurrence of the beta minus decay. First, we write the equation representing beta minus decay. To calculate the disintegration energy in the beta decay, we must find the mass difference before and after decay. The masses given are those of the neutral atoms, and we have to keep track of the electrons involved. The parent nucleus has 6 protons and 6 orbiting electrons because we suppose it is neutral. The daughter nucleus has 7 protons, so it is not neutral because it has the same 6 orbital electrons circling it. However, the mass of this daughter atom with its 6 electrons plus the mass of the emitted electron, which makes a total of 7 electrons, is just the mass of a neutral nitrogen atom. The neutrino does not contribute to either the mass or charge balance because it is neutral and its mass is approximately 0. This energy is shared as kinetic energy of the electrons and the antineutrino. In beta plus decay, a positron and a neutrino are emitted by a nucleus. The number A of nucleons remains the same, while the proton number Z decreased by 1 and the neutron number increased by 1. The general equation representing beta plus decay is given as follows. Inside the nucleus, a proton changes to a neutron, and to conserve the charge in the process, it emits a positron. The positron is identical to the electron except that it has a positive charge. Beta plus particle emission occurs when the ratio of neutrons to protons in the nucleus is less than 1 and the mass of the parent atom must be greater than that of the daughter atom by at least twice the electronic mass. In other words, beta plus decay generally occurs in proton-rich nuclei. Let's see how the beta plus decay works. Every carbon atom has 6 protons, so carbon 10 has 4 neutrons. It is unstable, and its ratio of neutrons to protons is 0.67. So this atom satisfies the conditions for the occurrence of the beta plus decay. We write the equation representing beta plus decay. Electron capture. Electron capture represents a decay process in which a nucleus captures one of its atomic electrons, resulting in the emission of a neutrino. Most commonly, the electron is captured from the innermost or K shell of electrons around the atom. For this reason, the process often is called K capture. Here, the atomic number decreases by 1 unit, and the mass number remains the same as positron emission. In this process, the electron is orbiting before it is getting captured by the nucleus. So it is as if it pulled working against the binding energy of the electron in the orbit. So that energy has to be taken into account. So for K capture to occur, the mass of the parent atom must be greater than that of the daughter atom by at least the binding energy of the electron. An example is beryllium-7 decays by electron capture to lithium-7. Pay attention. Gamma decay. Experiments have shown that protons and neutrons are located in discrete energy states within the nucleus, not too different from the ones in that electrons can occupy atoms. A nucleus may reach an excited state as the result of a violent collision with another particle. More common, however, is for a nucleus to be in an excited state after it has undergone alpha or beta decay. Thus, if a proton or a neutron inside of the nucleus jumps up to an excited state, generally following an alpha or beta decay, the new daughter nucleus must somehow release energy to allow the proton or neutron to relax back down to the ground state. When the nucleon makes this transition from a high to a low energy state, a gamma photon is emitted. We can write decay as follows. The asterisk means excited state of the nucleus. The following example shows the gamma decay process. Dangers of nuclear radiations. If radiation collides with or passes close to atoms, it may knock or drag electrons away from the atoms. The resulting atoms are said to be ionized, and the process is called ionization. And because radiation produces ionization, it can cause considerable damage to materials, particularly to biological tissue. Ions produced are highly reactive and take part in chemical reactions that interfere with the normal operation of the cell. The hazard levels are given in the table below. The following two examples are from IGCSE Cambridge Physics. You should try to solve them yourself, then check the answers. They are solved step by step.